Hello and welcome. As we're trying to finish up Chapter 5 for the gas laws, okay? And our last slide we were looking at, we looked at the kinetic energy and the velocity of the particles at certain temperatures, and we worked with that. I'm going to work on another problem over that, but that's going to be another video, okay? Here I want to finish off Chapter 5 as quickly as I can with you guys. When we talk about the range of velocities, if you stop and think about it for a moment, okay, there is a distance, an average distance molecules do travel before they go and crash into each other. And they do call it a mean free path. And yeah, it's very, very small, very, very small. And understand that when we look at temperature, which you could measure that as a form of kinetic energy, because heat is a form of kinetic energy. Remember that temperature is an average. If we look at the temperature of the human body, if we took the temperature from the toe to the ear to the mouth to under the armpit, you're going to get different numbers. So the reality is that temperature is an advantage. It's not an advantage, it's an average. And of course the molecules have many speeds in this average because not all molecules are going to travel the same velocity. Okay, and on this next curve here, you got the velocity distribution, number of particles, okay, and then the molecular velocity. As when you get to the higher number of particles, you kind of notice there seems to be a certain high at 273 K, where the particles, there's lots of them, and as the particles go down, they tend to travel a little bit faster. But if you stop and think about it, why is it that they're traveling faster when there's not so many particles? That's because they're not having as many collisions, because collisions would slow down the particles. Okay, here you are at 1273 K. All right, and you can see how that's going here. With the higher the temperature, it kind of shifts over more of that velocity, which would kind of make sense if you think about it. And here, that's not 1273 K, that's a higher temperature. Okay, but the idea is that the more heat that you're adding in there, the faster the molecules will travel. But it also makes a difference how many molecules that there are in there. Okay, so when we talk about the velocity, here's the bottom line. If you didn't understand the graphs, okay, as when the temperature goes up, the velocity is going to increase. There's more energy for those molecules to go and zip around all over. Okay. The spread will increase as the temperature increases. This is exactly what you're seeing. There's more of a spreading out here as the temperatures increase, but you have less number of particles there. All right, let's move on. We got to talk about gas effusion. And the idea of this is, imagine a gas going through a tiny little hole into an area that's a vacuum. The effusion rate measures how fast that this is happening. Now there is something called Graham's law, which shows us it's the rate of effusion is inversely proportional to the square root of the mass of its particles. So if we look at Graham's law, the idea is this: how fast the effusion rate is going, it's going to be depending on the mass of the particles. So if the particles are larger, they're heavier, then the effusion rate is going to go down. Because and stop and think about it, the heavier particles they're going to move, but they're going to be moving slowly because they're more massive, like carbon dioxide, for example. And if we look at hydrogen gas, H2 gas, that's very light if you stop and think about it. That is just going to zip out a whole lot faster. So that's the idea behind diffusion. Now, here's a visual for it where you've got a container, you've got two rooms, one is under a vacuum, the other has got the gas, and you have a little pinhole in there. So the idea behind that is that these gases, they are going to go through the pinhole. And depending, some gases will go faster than others. Smaller particles, smaller mass, they're going to go through faster, they're going to effuse at a faster rate than those particles that are heavier and more massive. Okay? We can talk about the rate of effusion is going to be proportional to the velocity of the root mean square speed. Okay? Why they chose U, I don't know, because basically velocity, it's a V, but we'll go with it. It is, they compared the effusion rate of the two different gases. that are there, which is equal to what their velocity, their root mean square speed is. That's what the U represents the speed, okay, and RMS stands for root mean square speed, okay. When we look at something like diffusion, on the other hand, diffusion is different from effusion because you're spreading the gas through a room. Imagine you're in a room full of people and somebody walks in, and within seconds you know that they're wearing a very strong perfume or a very strong cologne because you're on the other side of the room and you're smelling it. So what does that tell us? Well, the particles that have been evaporating off of the person's clothes or skin perhaps made its way through the room and it reached your nose. That's basically it. Okay, now it is slower, and if you think about it, it's comparative to effusion because molecules, they'll move at hundreds of meters per second. Now, of course, collisions with other molecules slow down the diffusions. Compared to effusion, when we're talking about going into a vacuum where there's really nothing there to block you, here in diffusion, we have got air, so you've got air molecules that are blocking the way, making it harder for those particles. The best estimate that we have in terms of the speed has to do with Graham's law. Okay? All right, let's move on. Okay. Now, real gases, on the other hand, they do take up the space. They interact with each other, especially when they are polar molecules. Remember, positive, negative for polar molecules. We do need to add correction factors to this ideal gas law to account for these. Okay. Volume correction, okay, the actual volume free to move in is less because of the particle size. If you have a bottle and you have a bunch of gas particles in there, remember, each particle does take up a certain amount of space. So that's why you have to have a volume correction. More molecules will have more effect. If you stop and think about it, more atoms, more molecules, they take up more space. Okay? We also talk a little bit about pressure correction as we're winding down here. Okay, yeah, the molecules are attracted to each other. The pressure on the container is not going to be the ideal because remember that PV equals nRT, that's the ideal gas constant. Here we're looking at how real gases behave. Okay, and of course the molecules are attracted to each other. The pressure on the container is not going to be the same as it is if it were an ideal gas. Okay, but it also depends on the number of molecules per liter. Okay, and of course, since two molecules are interacting, the effect has to be squared. Okay, and with that, I'm afraid that my time is over here on Chapter 5, guys. I'll do maybe one or two other videos dealing with some problem solving, but this is it. And I'll see you in Chapter 6.